get random, namely polynomials for related matroids. So we are going to define related matroids and then define a polynomial. So that in a certain sense can be considered an extension of Tutte polynomial for onto regular matroids. So let's first define the definition of matroid in terms of circles. So that in the finite set and so there are four requirements for first and the set is not in circles. Second, if C1 and C2 the surface and C1 these two it means that they're equal, and the last one is that if there are two circuits that intersect, so there exists an E in C capital such that in the intersection, then there exists another circuit such that twice in C1 union.
I believe the inclusion should be shown by a different sign. Знак включения должен быть другим.
So we call a subset of the dependent if it contains a circuit, independent if it doesn't. We call a subset of basis if it's a maximum independent subset. We call rank is a maximum number of elements in the basis of subset of other subsets. We call first circuit such subset of E that intersects every basis. Then we have certain matroids related to ours, and this corresponding to operations of deleting and contracting.
One moment, please. Значит, как нужно относиться к матроиду? Нужно представлять их себе так. У вас есть векторное пространство над каким-то полем. В этом векторном пространстве имеется конечный набор векторов. А дальше свойства этого набора нужно выделять свойства, отвечающие за линейную независимость векторов этого набора. Вот в этом определении в качестве основой выбирается свойство, значит, элемента нашего множества c, такое каллиграфическое, это максимально независимый набор элементов. So that in this case, for definition of a matroid, the property of being maximal independent subsets of vectors in a given finite set of vectors in a vector space is chosen. But one can choose rather different basic.
This example is nice, but it's misleading because in this case, all circuits has the same cardinality because of the dimension of the ambient space.
And that's the true for any matroid.
Okay.
This is not misleading. It is true that not each matroid, can be interpreted in this way, but not because of the.
So the list of axioms does not include that all circuits have the same cardinality, but it's a consequence of the.
It's a consequence. Yeah, it's a consequence.
And the rank is just this common number.
The rank of a matroid is just this common number, and the rank of a subset in a matroid is the dimension of the maximal independent subset. The number of elements of the maximal independent subset.
And the word independent exactly corresponds to dependence independence of vectors.
So yeah, we want to learn E. Well, what's called the edges, elements of E, and compare them. So we define following matroids. So for deletion, we have the same use, it's called downside, and its surface will be
those circuits of C that do not contain.
all the circuits don't contain actually.
This is a deletion operation.
Subtraction operation.
And according to your motivating example, the deletion operation preserves the rank and the contraction decreases by 1.
It should be like that.
So for contraction, we still the process still remains the same, and the surface we take.
So is it true indeed that the deletion preserves the same basic set, the same set E? In both cases, I believe we should eliminate. Если мы выкидываем какой-то вектор, то мы должны.
Well, I believe that for that's a good question, because in the paper for a normal matroid it was defined without deleting actual elements, and for oriented we actually do it.
Let's see, but if we take a set of vectors, when deleting a vector, we must eliminate it from the set.
It's logic.
Would you repeat how the contraction works?
So we take all the circuits and so the circuits are subsets of E, and we take each subset and take E away. So we take the set without all circles?
Один из главных источников матроидов это графы. И если у нас есть связанный граф, значит, E это набор его ребер, E это набор ребер графа, потому и обозначается буква E базовое множество матроидов, что мы обычно видим за ним набор ребер графа, и максимальное независимое множество это основные деревья в графе.
Если он связан.
Я сказал, что связано. Я сказал. We have a connected graph, and the circuits in the connected graph are
Spend.
Да, спасибо. A spanning tree, spanning trees are circuits in the graph. This basic set are spanning trees. If we contract an edge, then we just contract the spanning tree. We make the two ends of this edge a single vertex. So this is contraction. It works like that. Sorry.
So further we call the loop such an element of E that it is not in name basis, and we call element of E a call if it lies in every basis.
Значит, в терминологии графов копетля это мост. Это ребро, разрезание которого, удаление которого увеличивает количество. Петля это обычная петля, ребро, концы которого совпадают, а копетля это мост, ребро, удаление которого увеличивает количество компонент связанности в графе.
So now we define normal matroid, and we're going to move on to oriented matroids and look what happens there.
Again, the contraction reduces the size of the circuit. Contraction. So we have the circuit is a common number for the matrix. I just don't understand why. Matrix we have the vectors, vector space, and well, you have the same dimension. Then contraction reduced by one dimension.
It reduces the rank.
The rank, yeah.
Not the dimension,
the rank.
The rank, yeah. Reduced by one.
The deletion.
Deletion makes nothing. Normally it makes nothing to the rank. Yeah. Doesn't affect.
So for the oriented matroids, we are still going to have step, and our circuits will work a little bit different. We have circuits and they can look like this.
A is from arrow, I believe, yeah?
What?
Here you use the letter A to denote the basic set, yeah?
Yes. So x plus and x minus is the ordered pair of subsets of A, and they disjoint. And we call the Georgian has support of this. Now we need following axioms. Let's call it a main matroid N. In circles. So the first one stems from normal matroids. So the pair of two empty sets is not a circle. Well, we should also define set minus x, which is naturally the pair x minus x plus. So
The same pair, but
reversed. Well, we switch orientation.
change.
So the second axiom would be that for any circuit, minus subset is also so.
It's difficult to follow. Yeah, I see.
So this third axiom is going to be analog of the second one for normal matroids. So if we have two circles such that support of one lies in support of another, then they are either equal or
Opposite.
yes, is it equal or opposite? So, and the last one is going to be an analog for the third axiom of normal matroids. Well, it's going to be a little bit tricky. So, for any two circuits, so that are not the opposite.
What does it mean that x equals 1 and x is equal to the opposite of 1?
Either x equals y or
okay.
So, for any element in intersection of x plus and y minus, there exists such a circuit that pass lies in x plus y minus without the element, and so the analog for z minus is in x minus y plus without element. So, well, I want to say a few more words about the last one. So, we have pairs x plus y minus, x minus y plus, but we know that so if circuit lies in, so if we have if a set, the subset is a circuit, then the opposite is also a circuit. Well, this pairs, we can take opposites to cache these intersections. So if we would have a pair where x plus was intersect with y plus, we would just take the opposite of y and then still use this x form. And so to illustrate what's going on here a little bit better, I show a little bit of a graph example. So if we have,
you may also delete the
yes. So if we have a graph and we have two circuits intersecting, then so what the third external for normal matroid says is basically there exists another circuit of this type that we kind of glued together from the first two circuits. Now, what this says is that we can basically, for a moment, forget about orientation, then glue it together as without orientation, and then when we return the orientation, we would have to, well, we can see it. So on the edges, let's call it, from one circle, our orientation will remain the same, but on the edges from another circuit, we will have to switch orientation. So from here comes the fact that we have to postulate x plus unite with y minus and x minus unite with y plus.
Okay, sorry, I have to apologize. This definition of a matroid is not based on the notion of spanning trees in a graph. But a circuit is something which contains a loop. Circuit. Значит, это циклы.
Что, с каждым графом можно разные матроиды связать?
Нет. Определение матроида можно давать по-разному. Можно давать определение в терминах независимых множеств, и тогда это будут основные деревья там. А можно давать определение в терминах зависимых множеств, и тогда это будут циклы, подграфы, содержащие циклы. С это здесь подграфы, содержащие циклы. И вот это утверждение об обмене состоит в том, что если два цикла пересекаются, то мы можем, то существует какой-то третий цикл, который является частью, это можно считать, что это простые циклы, и существует третий цикл, который содержится в объединении этих двух и не задевает ребро Е, если оно общее для двух циклов, C1, C2. So that if C1 and C2 are two cycles, circuits in a graph, then and they have a common edge, then we are able to erase this edge, and the rest of these two cycles do contain a single cycle. That's what is the assertion. Now, what you are telling us is that oriented matroids correspond somehow to oriented graphs, or what? Как нужно думать про ориентированные матроиды? Верно ли, что они связываются с ориентированными графами?
Well, oriented graphs are a subset of oriented matroids, but not all oriented matroids are graphs.
The same is true for matroids and graphs. Each graph determines a matroid, but not all matroids come from graphs. But will you show somehow how to associate to an oriented graph an oriented matroid?
Well, so sure. So I'm going so one set will be a set of edges, and the circuits will be simple cycles with so on simple cycles we can define orientation in two different ways. So we can fix one edge, say that its orientation is positive, and then the edges that have the same orientation they go to positive, and the rest go to negative, and then we can reverse it.
Just draw some. Давайте пусть будет четырехугольник с диагональю. Можно? Ага. Exactly. Yeah. How D is oriented.
So here and so circuits follows. So the first cycle is BCA. So we have A, B oriented in the same way, and C is in the opposite, so it goes like this. So and we have minus the circuit. Then we have cycle C, D, E, and here they all oriented in the same side, so just
And empty, yeah?
yes, and empty, and then we have a big circuit, and well, first like this, and that's it. Normal cycles. This follows the circuits.
So the circuits are simple cycles. We can say which is C1, which is negative C1, but if we choose which one is C1, then the opposite will be negative. There are six oriented cycles, oriented circuits. Yeah.
So following notation, so we can take an oriented matroid and get a non-oriented matroid, obviously. So this way. So we, for each circuit, just take its apart and we will get it. Then
just forget orientation.
Just get orientation. So we have an orientation of a normal matroid. This well, we remember orientation from somewhere.
Can you always orient to what we don't? The opposite question.
Yeah. If you have a matroid, then are we able to make it into an oriented matroid?
No, it's not. Well, this paper says that it's not true.
It's not true. yeah?
What the matroids are. Then, well, so then we also have a few more invariant matroids that correspond to ours. So we, unlike normal matroids, we have three operations with our edges, so which are deleting and tracking, as previously, and also change the orientation of the edge, rearrange.
Yeah, and when we change the orientation of an edge, then it switches between the positive and the negative part, yeah?
Yes.
For example, change the orientation of A, then it will
Yes, it
move here and then
yes, it will go like this. So, all right, let's go with first, and then there will be examples to show so now we have a invariant matroid, and we have the most important function we work with. It's called Q flow or поток, and
какой поток?
Q поток, flow, Q
Поток.
flow.
Q,
Ну, если
just right. Q поток.
So this such a function from one to
Стирайте до конца, тогда старайтесь.
that satisfies for all circuits. It satisfies the natural restriction that some of well, basically an oriented sum of edges is zero, so it's sum over
oriented sum of edges at each vertex should be zero, and we don't know what is the vertex.
well, it's just a bit of so that's a formal definition. So for each circuit, well, we have a subset that's positive, and we take some functions at this point, and then we take some functions in negative points.
So this is indeed not a flow, but a coflow. Значит, что такое поток? Поток – это такое распределение тока по векторам, что в любую вершину сколько втекает, столько из нее вытекает. А это копоток. Копоток мы распределяем токи по векторам таким образом, что на каждом цикле сколько течет в одну сторону, столько течет и в другую. So that it is indeed a coflow rather than a flow. In each circuit, what goes one way goes the other way too. The same amount of flow goes the other way.
Well, so let's give an example. I have an example for homes. So just another graph. It's similar to this one. So this So surface here will be and we are going to look for all possible flows, the Puka flows. So well, DC
The first circuit.
CD. So the first circuit is like this.
No,
But ABD.
Yeah, no, it's the first
ABD,
one.
yeah, it's, yeah.
So the first circuit is
Absolutely correct.
this one.
No, I just didn't see.
Now, so what kind of Puka flows can be here? So let's say Puka flow on the edge A is equal I, and the edge B is equal J. Then we know that on edge D it's equal minus I minus J, and on edge C it's equal I plus J. And for any I and J we get a Puka flow where I and J are basically smaller here. So we get who squared Puka flows. So then for every Puka flow, it's important for us to know certain values. The first one is the number of edges, elements of this set in program set, where f of a lies in such a set, from 1 to half of course. So we take always this model Q and we take the first half of it. And that's, we count the number of edges where our functions, our flow takes the this one.
Сейчас, а нолик сюда не входит, да?
Нолик сюда не входит. Zero. Then, so we have the pair of it where it's for going like this. So this is the number of edges where our function is from basically Q half to Q, and then we have a number of edges where it's 0.
You need just another, the right bracket in the previous part.
So, and now we are ready to define a polynomial that we want to define so much. So we claim that there exists such a polynomial of 3 variables that such that for any odd integer q greater than 0, is going to be equal to the sum over all q flows. We are going to define the set of all q flows with capital F. And here is also this. And so we take each hook of flow, we count the number of edges in which it takes both says positive, having positive numbers, and so we take y to the power, then we count the number of edges where f is negative, and this was to the whole is negative, and you take z to the power, and then we sum over all future flows.
А что индекс n обозначает? N это ваш
Yeah, n is our oriented matroid.
Oriented matroid. So a matroid is denoted by n, and an oriented matroid is denoted by n. Great. Значит, если у нас есть обычный граф, то его мы можем сопоставить его потоковый многочлен. Он зависит от одной переменной, перечисляет потоки, всюду ненулевые потоки со значениями в группе из бабелевой группе из m элементов, ну, например, в группе, ну, скажем, из q элементов в группе вычетов по модулю. So that for an ordinary graph, we are able to take its flow polynomial, which enumerates everywhere non-zero flows. In this graph, a flow is to be more precise. Здесь все-таки требуется более точное определение. Мы берем граф, выбираем на нем какую-то ориентацию и расставляем на ребра этого графа вычеты по модулю Q. Ненулевые вычеты по модулю Q. Такая расстановка называется потоком, если в любую вершину сумма втекающих вычетов равна сумме вытекающих. It happens that this way to assign a flow to each edge of the graph, first of all, does not depend on the chosen orientation. This number, second, is a polynomial in Q. It is a polynomial in Q is the number of possible values of the flow. Here we have a more refined version for the oriented case, where we have a polynomial not in a single variable but in 3 variables. Additional information which encodes this polynomial is information about the number of big residues of edges with big residue and the number of edges with small residues, y and z. But in spite of the fact that this is not obvious from the definition, this is also a polynomial in Q. it's obviously a polynomial on y and z, but it's in fact a polynomial on q as well. Great. And is this a type polynomial?
Well, yeah, it's polynomial was okay. Yeah. Now, well, so let's.
Это тот самый многочлен,
Да,
который,
тот самый многочлен, который выходил.
который в названии статьи, да?
Да. Здесь, well, I have to tell this polynomial not defined on all real matroids. It's only defined on regular oriented matroids. And I also teach a regular matroid. So we know that the matroid can be represented by matrix. And if a matroid is represented by totally modular matrix, so such that so all determinant of
for oriented graphs, we always obtain
yes, for oriented graphs. So the happy part is the graphs good. So it's kind of like reciprocal. It's a little bit more. So
probably then we will not seek for precise definition. Okay.
So oh yeah. So yes, it's not a polynomial. So basically, it's a point. Yeah. So we need to take inverse matrix at some point. And well, it's good if it's totally modular, because then well, inverse matrix is good, and if it's not, then it's not. So let's talk about the relation between the polynomial explode and the actual Tutte polynomial. So it is very connected to what's polynomial, which is the same as Tutte, but with changed variables. So, well, Tutte polynomial. Is it Tutte or Tutte?
Владимир Ильич Арнольд говорил тут-то. Я предпочитаю говорить так-то. I'm not quite sure which pronunciation is the correct one. This is the type polynomial for ordinary matroids. It depends on two variables, x and y.
And what's polynomial? Is it from false? And Can it be seen or
I see.
Everybody can see in the screen. Yeah, that's great. So we find complex polynomial through that polynomial, and well, it's easy to change this universal change of variables. So as long as we connect our polynomial to a complex polynomial, it will automatically mean that we connect it with that polynomial.
Вообще многочлен Потца был придуман в качестве одной из моделей статистической физики. Такие простейшие модели, как всякие простейшие модели, они чаще всего работают и чаще всего встречаются в самых разных ситуациях. И многочлен Потца – это вещь, которая измеряет энергию. Значит, там речь шла, какой же там лед, не помню, бинарный лед, и мы плоский лед мы кодируем плоский лед такой решеткой, обычной решеткой, и в каждую точку решетки вставляем вектор, смотрящий либо вверх, либо вниз. В зависимости от этого на каждом ребре графа, у каждого ребра графа появляется энергия, зависящая от того, два вектора на концах этого ребра смотрят в одну сторону или в противоположную сторону. А затем мы суммируем по всем способам расстановки этих векторов, и в зависимости от того, какая получается сумма, значит, у нас энергия соответствующего графа или соответствующей решетки определяется. Sorry.
So now I'm going to write statement of the so the polynomial is also equal to such a set of all Tutte flows. So we take a regular invariant matroid M, and then we take an orientation and of M, and well, here we use the fact that it's regular to say that such an orientation exists. So the lemma says that what's polynomial equals the sum over all Tutte flows of an vector of y to the power. Well, it's take analogy with previous. So what was taught previously, and so that's a number of edges that on which Tutte flow does not take is number 0.
And this is independent of the choice of the orientation, yeah?
Yes.
It's independent of the choice of the orientation. Yeah.
Well, yes. Well, presentation doesn't change 0, so it's independent. So we have. Well, so I'll rewrite this position. So as a consequence of this dilemma, the whole three properties. So the first one is false.
What will be the z in the false polynomial?
Sorry?
The z, the third variable in false polynomial.
There is no.
Because in your first constituent, you say.
Oh yeah, there is no comma. It's y multiplied.
Okay.
It's y times z.
Yes, it's y times.
Two variables.
And q is always odd.
No, no. So the way we handle it is that we know that it's a polynomial, and so we for equalities hoping to prove an equality in infinite series of points where q is odd, and as such claim that they equals polynomials. Well, what it is? Well, so first one is just, well, it's already a connection, so we know that it's so reasonable. A second.
Please speak louder.
Yes, right, I kind of lost it. So I want to understand why this is called valuable if I wrote it correctly. So right, let's start doing this, I think. Alright, let's start doing these things. We are going to start from the third one. It's just the direct consequence dilemma. So if we
By the way, can we understand this as that for this Q for flow polynomial, we have something like deletion contraction relation.
yes, we do have such a relation.
And then we can proceed by induction.
Well, we can't proceed by induction because there. So we have for oriented matroids, we have a third matroid related to others, that is reorientation matroid. So when we have an equation, then we can just find our matroid. We will have a sum of matroid that reorient matroid, and so we can get reduction.
And will you please write down the deletion construction?
Yes.
So that then, since we know that the Tutte polynomial satisfies deletion contraction, and we know also that Fuka flow satisfies deletion contraction, then we can believe that they are indeed reduced to one another.
So here we reoriented one edge. And it equals x plus that. Then we delete an edge. Plus 2 minus x minus z multiplied on polynomial with contracted edge. So this inequality. So the short, because of this thing we can just young induction and counter calculate, but well, it becomes pretty useless actually. That's useful.
It's not a reduction, yeah? Мы не можем по индукции.
Да, мы не можем пойти по индукции, потому что, да.
Потому что два члена слева.
Да, два члена слева, и их никак не сдается.
That's rather interesting. Well, but still you were planning to.
I was planning
to give a proof, or at least a hint of a proof.
Well, the lemma, not proof lemma, I can figure it out. So let's go proof, and I hope you understand why this is good anyway, because I'm afraid it got something wrong. So the last one is just the White's definition on the left part. It's sum over all clause y to the power and we know that by lemma we know that it's equal to
whether the index of A should be capital N. Нет, вот в предыдущей строчке А у вас с индексом N большой должен быть.
Да. Yeah. So we'll just get directly, then what are you going to do? So let's look at, can I?
All right.
So we will write the right part through the lemma, and we will insert the proof the following. Yeah. Fix. So yeah, I did write it correctly. So here, so what is like M with error? So we take a matroid, and for each edge, we take and double it, and we take one with one mutation and the second with another mutation. So basically, we for each edge we take create two edges, and we take a circuit. So it was we go from a normal matroid to something like this. Now, well, then this equality basically means that, so why it's important for us, because it says that what we are writing is actually the correct extension of that polynomial on some matroids oriented on the regular oriented matroids. It's just not something close, but actually, if we take a kind of reduction on normal matroids, then we are going to get exactly that. Well, it's not that polynomial, but something that we understand what we already understand. So and so and the brackets do it first, and then I'll get back to the second. So yeah. So we want to take a projection between all circuits here, where we will use as follows. Well, basically, we know here that for these two.
Don't address me.
Yes.
Address you.
So for the two opposite edges, their values are opposite. So we know that for each pair of for each pair of opposite edges, there will be they either both going to be 0, and then they're going to give us multiplier 1 both in the left part and in the right part, and or they're going to be 1 give us a multiplier, all they have because multiplier yz both to the left part and to the right part. And there is natural projections between circuits in these two matroids, and so we have this equality for each circuit, so then we hold both. So
You choose some basis of circuits, or you work with also circuits together. Вы выбираете какой-то базис среди циклов? Базисные циклы какие-то?
нет, мы здесь не выбираем циклы, мы просто говорим, что у нас нет, ну просто у нас понятным образом циклы отсюда ассоциированы с циклами отсюда и
взаимно однозначно.
да, это очень. Мы просто расклеивали, расклеиваем их обратно, и множители просто вылезают одинаковые, потому что мы их определили. Вот. So it's those, and so there's only one word left. So the reason this one is kind of important is because it shows that our polynomial A remembers something about polynomial, about that polynomial. So it says that structures that kind of built in that polynomial, they can, so we can hope and to discover them in our polynomial too. So proof. Well, yes, right. So we take a sum over all orientations of that. So we took a non-invariant matroid, then took a sum over all its orientations. So
So you take the average of all possible orientations. Yeah?
right. So well, because it's a regular matroid, we know that any orientation is actually works of this. So we fit one orientation, and then we just start reorienting on the subsets of ground set. So it's goes sum over all the subsets of, so we reorient all the subsets, and then so, and I want to say that yeah, so we rewrite this by definition, we get a double sum. Some of the few flows and some of the subsets. And so we want to say that it equals to 2 to the power of well, so this sum equals to the power of so here. So basically we say that if on, so we fixed a Krupka flow, and if there is an edge on which Krupka flow takes the value of 0, then well, so we take that as a product for each edge, and for edge on which we have a value of 0, we have multiplier 1 plus 1, and then for others we have multiplier of x plus y. And so if we open the brackets, you will just get the sum just over notations. So it's this product is 2 to the power of, well, number of zeros multiplied by y plus z to the power of number of non-zeros.
Okay, and probably we should stop here and you for very clear and in fact interesting talk. Let me ask my usual questions concerning this object. So we have this is an invariant of oriented graphs. Linearly. Yeah? An oriented graph is a cluster. It's equivalent. How does it behave with respect to equivalent mutations?
Здесь у вас различается, если кратный ребра, он как-то не реагирует.
Да. Конечно, вот это. Здесь example.
А сокращение, если в одну другую сторону, тут нет уже.
Тут нет, да. Но тут нет, но может быть можно изготовить какой-нибудь вариант. One of the problems in the theory of cluster algebra is the lack of invariance of mutations. Could it be that one can make an invariant of such something which is invariant under mutations, something which is invariant under mutations from that polynomial? That's one problem. The second, one question. Question number 2 is that comes from the theory of oscillative invariance, and we have a code diagram, and we may associate to it its intersection graph with a code diagram. Intersection graph. Graph which is non-oriented. It's non-oriented. However, we're also able to pick an orientation by making the code diagram into an arc diagram. Something like that. Enumerating codes according to the order of the left hands. It would be something like 1, 2, 3, 4, 5, something like that. And orient each edge from a smaller end to the bigger one. In this way we obtain an oriented graph, and it happens that some invariants related to this oriented graph become invariants, become weight systems. Like, for example, the characteristic polynomial polynomial of the skew symmetric adjacency matrix of this oriented graph. If you take a non-oriented graph and take its adjacency matrix and take its characteristic polynomial, then this characteristic polynomial has nothing to do with Vassiliev invariance. However, if we orient this graph in this way, not arbitrary orientation will do. Only orientations that can be obtained on the graph by choosing the corresponding cut point. Then we obtain an oriented graph in this way, and then this characteristic polynomial of the skew symmetric adjacency matrix becomes a very nice Vassiliev invariant. Whether the same as something similar is true for this polynomial.
Can one extract weight system from oriented intersection graph? Record diagram.
By means of this
This is just polynomial of oriented intersection
matroid, of oriented intersection graphs. We take this this Q flow, this one is easy to verify. We just take small examples and check whether we have something like that. And
how does it? How it behaves on if you change the cut point?
This characteristic polynomial remains unchanged.
Yeah,
But what happens is, yeah, of course. Of course, it's, this question makes sense by itself. Yeah, point, right? Thanks, Georgii. It's very nice. Thank you. Are there any questions, comments? If not, then let's make a break.